Short-circuit currents can cause significant damage to electrical components and then generate dangerous situations for human safety. Perhaps the best way to describe the available short-circuit current in an electrical system is by means of a water analogy. The water being held back by the dam represents the short-circuit current, whereas the normal flow of water through the dam is analogous to the full load current in an electrical system. The floodgate would be comparable to a current-limiting electrical protective device, providing protection for downstream dwellings or electrical system components. Should the dam rupture, this would be like an electrical short circuit, allowing the entire reservoir of energy to suddenly flow downstream. The floodgate holds back a portion of the damaging flow. This let-through energy is less than would have occurred otherwise, thereby providing improved downstream protection. All of the devices used in this film are high-quality electrical components. It is not the intention of this film to in any way denigrate these products. The intent is simply to show the comparative protection capabilities of various electrical protective devices. Short-circuit currents can lead to significant electromagnetic forces in an electrical system, thereby causing mechanical damage to electrical components and reducing electrical system life. Magnetic forces vary with the square of the peak current. The large red area diagrammatically represents non-current limiting protection, while the smaller green area represents the magnetic forces that result with a current-limiting protective device. For this first set of comparative tests, we have a length of conductor exposed to an available fault current of 15,000 amps, 480 volts. The three protective devices, all nominally rated at 25 amperes, are conventional circuit breaker, current-limiting breaker, and current-limiting fuses. The first test is the non-current limiting breaker. Again in slow motion. The magnetic impact on the conductor can lead to significant potential mechanical damage to the cable. The second test is the same, except with a current-limiting breaker. Note the larger size of these more costly devices. Again in slow motion. The amount of magnetic whipping has been reduced, but is still significant. There is still potential mechanical damage to the conductor. The third and last test, with exactly the same test parameters, employs current-limiting Class J time delay fuses. There is little or no magnetic movement of the conductors. The fuse's high level of current limitation provides superior mechanical protection to conductors. The other potentially damaging effect from fault currents is thermal damage. Thermal energy varies with the square of the RMS current multiplied by the clearing time of the protective device. The large red volume diagrammatically represents non-current limiting protection, while the smaller green volume represents the thermal energy that results with a current-limiting protective device. For this set of comparative tests, we have a short piece on low ampacity conductor exposed to an available fault current of 15,000 amperes, 480 volts. The three protective devices, all rated 25 amperes, are conventional circuit breaker, current limiting breaker, and current limiting fuses. The first test shows the non-current limiting breaker. The thermal impact on the small conductor is obvious. Again in slow motion. The breaker has operated as intended, with its handle in the trip position. However, the small conductor has completely vaporized. The second test is the same, except with a current-limiting breaker. Note the larger size of these devices. The thermal impact on the small conductor is once again obvious. Again in slow motion. Although the energy may have been reduced with the current-limiting breaker, the let-through energy was still greater than the withstandability of the conductor. The third and last test, with identical test parameters, employs current-limiting Class J time delay fuses. There is no damage to the small conductor, since the let-through energy was less than the withstandability of the conductor. The fuse's high level of current limitation provides superior thermal protection to conductors, thereby maximizing electrical system life. Whatever type of protective device is used in an electrical system, it must have an interrupting rating greater than the anticipated fault current. 4 tests will be run, all with a fault current of 25,000 amperes, 480 volts. The first 2 tests will show the results of an inadequate interrupting rating. These are misapplications and contrary to the electrical code. The first test shows a breaker with an inadequate interrupting rating of 18,000 amperes exposed to a 25,000 ampere fault. The result of this misapplication is as expected, a violent explosion. The second test shows fuses with an inadequate interrupting rating of 10,000 amperes exposed to the same 25,000 ampere fault. Predictably, the fuses also explode as the result of this misapplication. The third test shows a breaker with adequate interrupting rating of 35,000 amperes exposed to the 25,000 ampere fault. The breaker opens safely. Again in slow motion. The ionized product that you see in this test is the normal outgassing of a circuit breaker through its arc chutes. The fourth and last test shows fuses with adequate interrupting rating of 200,000 amperes exposed to the same 25,000 ampere fault. The fuses open safely. Fuses are sealed devices. Resultantly, there is no outgassing to the surrounding area. As well as being adequately rated and providing optimal protection for system components, it is also desirable to minimize the disruption to an electrical system when a fault occurs. Ideally, the goal is to isolate the faulted circuit while all non-faulted circuits remain energized. This is referred to as selectivity and minimizes system blackouts. 6 tests will be run, with various protective types connected in series, respectively rated 200, 50, and 25 amperes. A downstream short circuit closing switch will initiate the fault. The first test consists of an older 200 ampere breaker with modern 50 and 25 ampere downstream breakers. This scenario represents the addition of a new feeder to an existing installation. The instantaneous trip settings for the 200 ampere breaker are set to maximum, which would be approximately 10 times nominal rating, or 2,000 amperes. Above this level, the main breaker will operate in its short time trip range. The fault circuit is 15,000 amperes, 480 volts. The lights represent the main and feeder circuits, with the closing switch creating a fault on the branch circuit. The result is that all three breakers open, causing a total system blackout. This could be predicted, since the fault current of 15,000 amperes is well above the 2,000 ampere instantaneous trip of the main 200 ampere breaker. For the second test, the main 200 ampere breaker was replaced with a modern breaker that includes a short time trip delay, which is overridden at approximately 10 times the instantaneous trip of the breaker, or 20,000 amperes. Therefore, for any faults below this level, the breaker has the short time trip delay. The result is that the branch and feeder breakers open, causing a partial blackout. This could be predicted, since the fault current of 15,000 amperes is below the short time trip delay maximum of 20,000 amperes. The third test is the same as test 2, except that the fault current has been increased to 25,000 amperes. The result is that all three breakers open, thereby causing a total system blackout. This could be predicted, since the fault current is above 20,000 amperes where there is no short time trip delay. The fourth test has the branch breaker changed to a current limiting type to reduce the fault current due to its current limiting capabilities. By doing so, it is hoped that one or more of the upstream breakers will not needlessly open. The result is that the branch and feeder breakers open, causing a partial blackout. The fifth test shows North American Class J time delay fuses. Selectivity could be predicted, since the North American minimum selectivity ratio between these fuses is 2:1. Maintaining this minimum ratio ensures selectivity for all fault levels up to the interrupting rating of the Class J fuses, which is 300,000 amperes. The result is that only the faulted branch circuit is de-energized, allowing the non-faulted main and feeder circuits to remain fully operational. The sixth and last test shows European fuses mounted in compact modern-day switches. Selectivity is again predicted, since the European minimum selectivity ratio between fuses is 1.6:1. You are able to see a reflection in the clear plastic cover of the branch switch when the downstream fault is initiated. The result is that selectivity is once again achieved. Fusible protective systems provide simplicity, current limitation, and selectivity. An argument that is sometimes forwarded in support of circuit breakers is that they can be immediately reclosed after they have operated. The following tests demonstrate the repetitive or multiple use of a 25 ampere breaker. The interrupting rating of the breaker is 50,000 amperes, which is twice that of the 25,000 ampere fault that is applied. Between each operation, the breaker is allowed to cool and is mechanically no-load exercised 3 times before the fault is reapplied. Continuity measurements are taken to confirm the ongoing functionality of the breaker. The first test shows that the breaker operated within expected performance parameters. The second test shows some evidence of an ionized product, indicating degradation within the breaker. During the fifth test, the amount of ionized product has again increased, indicative of aging. During the eighth test, significant ionized products are evident. After this test, continuity testing indicated that the breaker was no longer conductive when the breaker was reset to the closed position. This occurred even though the handle still functioned with a good audible clicking sound generally associated with a functional breaker. This is a freeze frame of the 8th and last test. When utilizing a multiple-use device, the key thing is being able to know when that device can be safely reused. For these comparative tests, an arc has intentionally been created on the bus, immediately below the protective device by means of a small piece of copper wire. Magnetic forces will tend to push this arc down the bus. The protective devices used are all nominally rated 400 amperes. The devices are an airframe breaker, molded case breaker, and current-limiting fuses. In all three tests, the fault current is 20,000 amperes, 600 volts. The first test shows an airframe circuit breaker. The freeze frame of this test shows that the arc has migrated almost the entire length of the bus. The second test shows a molded case breaker. The freeze frame of this test shows that the arc migration is significantly less, the result of a faster opening time. However, notice the size of the arc for comparison to that of the third test. The third and last test shows current-limiting time delay Class J fuses. The freeze frame of this test shows the significant reduction in not only the migration of the arc, but also the size of the arc. Fusible protective systems enhance system protection for high-magnitude arcing faults. One of the most common electrical components used in the industrial field is a motor starter. In this comparative test, the fault current is 25,000 amperes, 480 volts. The IEC type starter used is a high-quality device. It is a brand that is well respected and extensively used in industry. It is being misapplied by being closed in on a faulted circuit. These tests are in no way critical of the starter, but simply a comparative analysis of the protection level for the various protective devices associated with it. The protective devices are a conventional breaker, current-limiting breaker, and current-limiting fuses. All have been properly sized for the application. The first test shows a conventional circuit breaker with a new starter. The fault is initiated by using the starter itself to close in on the faulted circuit. As you can see, the contacts are fully functional before the test. The ionized product can be seen outgassing from the breaker's arc chutes as it opens the circuit. Inspection indicates that the starter contacts appear to be welded. The protection level is Type 1 protection, meaning simply that the component damage is restricted to within the component and that the component is not reusable. Upon closer inspection, it can be seen that the welding was extensive and that the contacts are unable to be pried open. A freeze frame at the point of contact closing indicates the extensive energy that ultimately led to this welding phenomenon. The second test shows a current-limiting breaker in the hopes that the current limitation will improve the protection level rating. Identical test conditions are used. A new starter has also been installed. Once again, the contacts are fully functional before the test. Although the amount of outgassing is significantly reduced, the starter contacts again appear to be welded. Upon closer inspection, it was determined that the contacts were unable to be pried open. With a freeze frame, it can be seen that the actual fault energy has been reduced. Nevertheless, the protection level remains Type 1 protection. The third and last test shows current-limiting Class J time delay fuses. The test is identical to the prior tests, with a new starter once again used. The contacts are fully functional before the test. With all of the preceding fuse tests offering such exceptional but uneventful protection, we decided to add lights to this test, simply to confirm that the circuit indeed experienced a fault current. The starter is protected. The contacts continue to be fully functional. The actual energy let through by the fuses was below the withstandability of the starter. The protection level achieved is Type 3 protection, meaning that there is little or no damage to the component and that it can be immediately reused. The purpose of these tests is to explain the differences between fast-acting and time delay fuses, as well as to clarify any possible misconceptions about time delay fuses. For inrush applications like motors, transformers, and solenoids, the thermal capacity of a fuse in the overload region determines how it should be applied. The goal is not only to avoid needless openings on temporary harmless overloads, but also to ensure proper protection against longer, dangerous overloads. The solenoid is a good representation of inrush applications, drawing significantly more current while the solenoid closes before settling back to its normal running current. In these tests, a 1 ampere solenoid is used. For the first test, a fast-acting fuse is employed at 125% or 1.25 amperes. When energized, the fuse opens before the solenoid has fully closed. The fuse lacked sufficient thermal capacity to allow the solenoid's normal inrush current. For the second test, another fast-acting fuse is used, but sized higher at 300% or 3 amperes. This allowed the solenoid to repeatedly close, since the larger rating increased the fuse's thermal capacity. However, consider the fact that we now have an oversized fuse in the circuit. For the third test, a time delay fuse is employed at 125% or 1.25 amperes. Like the 3 ampere fast-acting fuse, this allows the solenoid to repeatedly close, but the fuse is sized much closer to the solenoid rating. This is possible due to the additional overload capacity of time delay fuses. For the fourth and last test, we will demonstrate the level of protection offered by the same 1.25 ampere time delay fuse when a serious and potentially harmful circuit condition occurs. Similar to the locked rotor condition of a motor, we have blocked the stroke of the solenoid with a spacer. The so-called time delay fuse operates quickly to de-energize the abnormal circuit condition. Time delay fuses can be used for both inrush and non-inrush applications. They are ideal all-purpose fuses for an electrical distribution system. Protection of ultra-sensitive solid-state electronic devices is a specialty area, requiring ultra-rapid fuses with faster overload capabilities and a higher degree of short-circuit limitation. Some semiconductors, such as large IGBTs, cannot be fully protected for all levels of overcurrent. The failure mode of an IGBT can be quite dramatic. The first test demonstrates the failure mode of an IGBT when not protected by a current-limiting device. The ionized products are significant, potentially causing serious collateral damage to adjacent circuit components. The second test shows the same circuit conditions, with the only difference being the addition of an ultra-current-limiting semiconductor fuse. While the fuse is unable to protect the functionality of the IGBT, it is able to at least provide Type 1 protection, such that the ionized products are contained within the IGBT housing. In this way, adjacent circuit components are not exposed to explosive end-of-life scenarios.